Hello everyone, I am Bhumika and today we are learning some questions related to numerical data analysis. So let's begin. Hello everyone, today we are learning the Gaussian elimination algorithm to solve simultaneous linear equations step by step. Step 1, start. Step 2, input the number of equations n and the augmented matrix A by B. Step 3, forward elimination. A for k equals to 1 to n minus 1, I for I equals to k plus 1 to n. Calculate factor and update row using Aij equals to Aij. In this step, we make all the values below the main diagonal 0. We loop through each pivot row using k. Then for every row below it, we find a factor which tells how much we need to subtract. Update the row using this formula. Aij equals to Aij minus factor into Akj. This steps gives us an upper triangular matrix where all values below the diagonal are 0. Step 4, back substitution. Once we have the upper triangular matrix, we find the values of x, start from the last equation and go upwards. We calculate each variable using subtract the known values from the right hand side. Then divide by the diagonal value. This way we get all the values of x1 to xn. Then output. And step 6, end. Now explain pivoting and solving simultaneous linear algebraic equations and why it is needed. Now what is pivoting? Pivoting is the process of rearranging the rows or columns of a matrix to place the largest absolute value in a column, that is called pivot element, at the top before applying elimination steps. Usually we do row pivoting, also called partial pivoting, where we swap the current row with a row below it that has the largest absolute value in the current column. Why is pivoting needed? First, to avoid division by 0, if the pivot element, that is diagonal element, is 0 or very close to 0, division will lead to errors or undefined results. Second, to improve accuracy. Using the largest possible pivot reduces round of errors in calculations, especially important in computer-based solutions. Third, to ensure numerical stability. Without pivoting, the Gaussian elimination method can give incorrect result due to small pivot values, leading to large computational errors. Now we have third question. Explain what ill-conditioned simultaneous linear algebraic equations are and how to solve them by refining Gaussian elimination method. So, ill-conditioned systems are sensitive. A tiny input change causes a big solution change. This happens when equations are almost dependent or determinant is close to 0. Example, x plus y equals to 2, 1.0001x plus y equals to 2.0001. This system seems normal, but subtracting both equations gives 0.0001x equals to 0.0001 equals to x equals to 1 and y equals to 1. Now change 2.0001 to 2.0002, that is 1.0001x plus y equals to 2.0002 equals to 0.0001x equals to 0.0002, that is x equals to 2 and y equals to 0. Just a 0.001 change caused a big jump in x from 1 to 2. That's ill conditioning. Now, how to solve it by refined Gaussian elimination method. To solve them accurately, we use refined Gaussian elimination with partial pivoting, where we find the largest element in the pivot column, swap that row with the current rows, then continue elimination. This reduces round of errors and improves numerical stability. Next question. Write an algorithm to solve simultaneous linear algebraic equations using Gauss-seidal iterative method. So, step 1, start the algorithm. Step 2, input the number of equations n. Step 3, enter the coefficient matrix A, which is an n by n matrix containing the coefficient of all variables. Step 4, enter the constant vector B, which contains the right hand side values from each equation. Step 5, enter the maximum number of iterations allowed and also the error tolerance epsilon, which defines how accurate the solution should be. Step 6, input the maximum number of iterations, max iter, and the error tolerance epsilon. Step 7, repeat the following step for k equals to 1 to max iter. Now repeat this loop for each iteration from k equals to 1 to the maximum number of iteration A for each equation index I equals to 0 to n minus 1. First, initialize sum equals to 0. Second, then for all j not equal to I, calculate sum equals to sum plus a ij times xj. Third, update x I as bi minus sum minus divided by a ii. Now step 8, after each full iteration check convergence. If x new I, x old I is less than epsilon for all I, then break. For all then, break it means if the change is less than epsilon for all variable, that means the solution has converged and we break the loop. Step 9, output the final values of x0 into x minus 1. Step 10, stop. Now next question, compare Gaussian elimination method with Gaussian-seidal iterative method and explain how to select the appropriate method to solve simultaneous linear algebraic equations. So, Gaussian elimination versus Gauss-seidal iterative method. In the basis of type, Gaussian elimination is direct method and Gauss-seidal iterative method is iterative method. Approach क्या है? Gaussian elimination solves equation in finite steps, while Gauss-seidal iterative method starts with guesses and improves iteratively. Accuracy, Gaussian elimination has exact solution in ideal conditions, while Gauss-seidal iterative method approximate solution depends on tolerance. On the basis of computational complexity, Gaussian elimination is higher for large systems and Gauss-seidal lower per iteration and scalable. Convergence. Gaussian elimination is always converse if solvable. Gauss-seidal iterative method only converges if system is diagonally dominant or well conditions. On the basis of memory usage, Gaussian elimination is high, need matrix storage and operations. And while Gauss-seidal iterative method, memory usage is low, update single values repeatedly, speed for large systems, Gaussian slower due to matrix operation, and Gauss-seidal iterative method faster for sparse or large matrix. Or suitability, Gaussian small to medium systems, Gauss-seidal large system with sparse matrix. Now, how to select the appropriate method? Use Gaussian elimination when you need an exact solution, the system is small or moderate in size, The matrix is not sparse and memory is not a concern. Now use gauss-seidal method when you can accept an approximate solution. The system is large and sparse, many zeros, which means the coefficient matrix is diagonally dominant or well conditioned. You need to solve systems quickly in real time or limited memory situations. Thank you and keep watching.